You're gonna ruin the shot if it's actually.
No, I'm saying we measured this length and we measured this length. And we do a squared plus b squared equals c squared.
Yeah.
B.
Yeah.
Yeah.
We do. How do you know this is the right triangle? Yeah.
Yeah, but
And plus, also he said this is not a right triangle.
All right, let me remind you about what we did last time.
I asked him what triangle.
We were talking about work. We said that work done by a force is equal to magnitude of a force times the distance that the object moves times the cosine of the angle between the force and that distance. We also said that total amount of work on the object, this is the work done by all the forces, would be equal to the kinetic energy. And a formula for this would be the final kinetic energy
we also
minus the initial kinetic energy. We'll write I here and an F here for that. And then our formula for kinetic energy was 1/2 m the speed of the object squared. Okay, that's basically what we covered last time. And we can do one more example before we do anything else. Let's say that we have a car with a mass of 1,800 kilograms. So, you know, roughly that's about maybe 3,400 pounds, something like that. Maybe 600. Maybe 4,000. Yeah. Okay, and the car accelerates from 25 meters per second to 35 meters per second. How much work was done on the car? Done. So this is done on the car. Well, if we could just go over here and, you know, since we know the maths and the speed of the car, we clearly know what the kinetic energy is going to be, right? So we can just look at the total work. It's going to be the change in kinetic energy, which would be the final kinetic energy minus the initial kinetic energy. The final kinetic energy is 1/2 m v final squared minus 1/2 m the initial squared. And then I can plug in numbers, right? In fact, I can make this 1/2 m v final squared minus b initial squared. Factoring it out, that usually saves one calculation. Kilograms times 25 squared minus 35 squared. Or wait, other way around, right?
Mm-hmm.
And then the units would be in joules. Joules. Like that. So what do you do when you get that? You get
I have 500 so
500,000.
yeah, 500,000. Yep, that's what I got.
500,000
540.
Yeah, 540.
Okay, 540,000 joules.
Yeah.
All right. Sounds good. All right, with that, so let me ask you something. What force did that work on the car? Just think about that for a minute. What force is doing that work?
Friction, wasn't it?
The friction force, yeah, not.
Yeah, so if I were to draw a free body diagram for this car, the work, if you want to increase kinetic energy, that work total, that has to be forces, external forces on the object. What that means is forces from outside the object being exerted on it. So what forces do we have? We have, normal force going upwards,
And then weight down.
weight going downwards. Neither of those will do work if it's moving in that direction, because the cosine of the angle in between the direction moved and this force would be 90 degrees. So there's only one other force on it, and that's the friction on the tires. So actually, the friction on the tires has to be pointing that way. And because this thing's, accelerating that way. So it's kind of an interesting thing just to think about that for a second. All right, let's go ahead and introduce another thing called power.
The friction wouldn't be pulling against the direction it's traveling?
The friction, no, it would be slowing down then, wouldn't it? Usually it would be, but in this case, if we're driving a wheel forward, the friction will want to
Oh,
oppose
the
that
drive is
motion.
coming from the wheels is where that
Yeah.
comes from. I
Because they're
follow.
going that way.
Okay, makes sense? A little bit tricky. Think about it for a little bit. All right, we'll do power now. So this is another thing. You have a lot of engine output figures and the power on the ground in cars. And what is that stuff? So let's say that I did a certain amount of work in a certain amount of time, total work done. Let's say that my change in kinetic energy happened over a period of time t. Time t. We're going to define power P as equal to the work, this is the power by a force, work done divided by the time it takes to do that work. That's how we'll define power. By the way, units of power, the units of the work is a force, is a joule, right? And then this is a
Second.
per second. So joules per second. That has a special name. Yeah, a watt. So that's a watt. And or W. Don't confuse this W with that work. Sorry, it's confusing. Work. Watt.
Is
Looks
it small
exactly the
W or a big W?
same. They're big W's
Oh.
in both cases. So you just have to, realize that this, keep it and get it from context, okay? So if this change in kinetic energy happened, say, in 5 seconds, there's only one force doing work on this object. And so I could say that the power total, which would be the power due to the friction force, is going to be that change in kinetic energy. That's the work done by the friction force, divided by the time it took to do that. I would take 54,000 joules divided by 5 seconds. And what would I get there?
108,000.
108,000 watts. Okay. by the way, there's a unit called brake horsepower, which is which is actually it means the horsepower applied on the ground like this. And a horsepower is somewhere on the order of about 700 watts. So you're talking maybe about 150 horsepower. Okay. So, and you can convert between those powers and whatnot.
Oh, so if we have horsepower, we have to convert it to watts.
Yes.
And what is the relationship?
Well, that's one I always have to look up.
Oh, okay.
I want to just look that one up. I didn't write that one down specifically. It's like 700 and something.
Okay.
Watts is 1 horsepower. Okay? Does that make sense to you guys? That power, you just take the work divided by the time it takes to do that work.
Are we gonna cover like potential energy here or not?
Oh, yes.
Okay.
Oh, yes. Potential energy, in fact, we're going to go do that right now. All right, let's talk about something called, well, let's talk about work done by gravity to start out with. Okay? Let's say I have a mass, and let's say that it falls from one height, I'll call this H1, to a second height, H2. What would be the work done by gravity in such a fall? Let's go ahead and see if we can do that.
mg8?
So the force of, the work done by gravity would be the force of gravity times the distance fallen
H.
times the cosine of the angle in between the distance and the gravity force. So let me just write this. The distance fallen is here, right? Because it goes downwards. The cosine of the angle, the force is also downwards. So to draw a free body diagram, I get mg downwards. So what's the angle in between the force and the distance? 0. And the force is mg. In terms of these h's that I gave you, what would the d be?
H1 minus H2.
8 minus H2.
Okay? That's it, right? This is the work done by gravity. Now, if I were to use my work kinetic energy theorem, I could see what the change in potential and kinetic energy would be, right? I could say that the kinetic energy final minus the initial kinetic energy would be the work done. And in this case, we have only one force doing work, right? So, this work done would be mg h1 minus h2. Okay? This h1 and h2, I could call this the initial height and then the final height, right? Maybe I should have done that to begin with. H at 1 is initial, H is F, I means initial, the starting point, F means final. And I get some sort of formula that looks like this, right? Well, here's something kind of interesting that you can do. This is just work and kinetic energy. But for this gravity force, you can end up rearranging this a little bit and write this in a different way. We can say that we can bring everything that involves a final over to one side and everything that involves an initial, an I, over to the other side. And what you end up with, if you do that, is you get the final kinetic energy plus mgh final is equal to the initial kinetic energy plus mgh initial. So this looks like something at the end is the same, looks the same as something at the beginning. What we usually do is we call this thing that's the same at the end as at the beginning, we call that the total energy E. And we say that, and for these gravity forces, this gravity force, we can say that this energy is conserved if the work is done by gravity. And we introduce this thing here called the potential energy. Due to gravity. And so this thing looks like, and total energy is the kinetic energy plus the potential energy, and that's the same at either initially and as it is finally. So we're just going to say that that's a constant. That's not that what we say. It just looks the same, you know, before and after. So we get that the total energy is kinetic energy plus potential energy. And this is the formula for potential energy in gravity. Now this doesn't work with all forces, introducing this thing called a potential energy. It doesn't work for friction forces. It doesn't work for, well, it doesn't work for a number of forces. It works for gravities and springs in this class, where we can introduce what's called a potential energy. And then say that the total energy is conserved. Okay? If you had other forces besides gravity doing work on the object, you can treat gravity as coming from a potential energy. So that just add the work done by other forces here. Okay, for kinetic energy is just this, and then add the work done by the other forces, and just go from there. The potential energy that we introduce, this MGH, just comes from looking at the work done by gravity. Okay, let's do some examples. By the way, one of the most amazing things about the special forces that you can introduce potential energy is that the work done by them only depends on the initial and final position. So I have the gravity force that went, the change of position that went from here to here. If I had taken a weird path so that this one went back up and then came back down to this position, the work done by gravity along this weird path would be the same as along here. We're not going to prove that. That just is something that is true for gravity forces. It proves a little more advanced. Okay? So let's go do some examples. Probably the easiest example is, let's say I have something falling down a hill. Let's say the height of this hill is h equals, well, okay, we'll do it with numbers to start out with. H equals 100 meters. Let's say it starts out at rest. When it gets to the hill, the bottom of the hill, what's its speed? So I'll do this one to start you guys out. So, as this goes down the hill, what are the forces on it? Let's ignore friction.
Gravity.
You have gravity and normal force, right? Normal force will never do work because it's always perpendicular to the direction it's moving. So we can say that the total work done is by gravity, and you can and we saw that total work. We can just introduce a potential energy if we're dealing with work done by gravity. So I'm going to say that the kinetic energy initially plus the potential energy initially is equal to the kinetic energy at the end, the final kinetic energy, plus the final potential energy. It really doesn't matter what I set as my 0 point for height. So I'm going to call this height equals 0 here, and this is just h. So initially, if it starts out at rest, what's its kinetic energy? 0. What's its potential energy?
MG.
GH, okay. What's its final kinetic energy? Right, 1/2 mv squared, right? And if it's down at the bottom of the hill and at height equals 0, what's its final potential energy? 0. Okay. So I can divide through this by m, and I get VH is 1/2 v squared. Could I get what v is? Yeah, pretty clear. So 2VH is equal to v squared. Take square root of both sides. So v is square root of 2VH. So in our case, that would be square root of 1,960 meters squared per second squared, which is what?
Do you have an estimate?
44.27.
Well, square root of 2,000 roughly, so it would be between
44.
40 and
Yes.
50.
Okay, 44.67.
44.3.
0.3 meters per second. See what I did? Now, you would have gotten the same result if you had treated this as just falling and figured out the speed when it got down to the bottom. This is really cool because it didn't matter what the shape of the hill was. Okay? And so even though we don't know exactly the sum of the forces at all points, we're still able, using this, knowing that only gravity is doing work on this, to use this kinetic energy plus potential energy being constant to get what the speed is. So these things are pretty neat. You want to do a couple other ones? Let's do a bunch more examples. Okay. Let's say I have a person, that throws a ball up in the air. Okay, the initial speed is at 10 meters per second. Okay. We can use this conservation of energy to figure out what its maximum height is going to be above where it was thrown. You can do this with kinematics and check it if you want, but this potential energy thing is going to be easier. So find the height that it gets up to. So height. Question mark. So clearly the only work done when it's being in the air is gravity, right? So let's start out with this, that the initial kinetic energy plus potential energy is equal to the final kinetic energy plus final potential energy. So what's its initial kinetic energy?
Yeah.
No,
It started, yeah.
It started at 1/2
MV squared.
mv squared, okay? Good. What's its initial potential energy?
MG.
Well, let's put h equals 0 here. as our 0 point, okay?
Ooh.
0, okay. What's its final kinetic energy if it gets to the highest point?
0.
What's its final potential energy?
MGH.
GH.
Okay. So I get that 1/2 mv squared is equal to mgh. I want to get what the h is, right? I can divide through by the m's. I can divide through by a g. I get v squared over 2g is equal to h. Okay. So if I plug in that would be 100 meters squared per second squared divided by 19.6 meters per second meters squared, which would be on the order of 10 meters, or not 10 meters. How many meters? 5?
5.1.
Good. See what I'm doing? Let's go try some other stuff. Oh well. Just have to get used to this. Let's go ahead and do something else. Let's do one now where we have a ball being thrown up in the air. Okay, so let's say that when it's a height 10 meters above the ground, its speed is 20 meters per second. So it's thrown pretty hard. And this ball goes up, comes back down, and right before it hits the ground over here, right before, what's its speed? So go ahead, give that one a try on your own, okay? I'll give you guys about 5 minutes, or 3 minutes. Shouldn't take you that long. You guys get it? Got it?
didn't take it.
All right, what do you guys get?
14.69.
I got 7.8.
I think it will have to be bigger than 20 because it's
It
fall.
has to be?
24.4.
24.4. All right, let's go ahead and see where this comes from, okay?
Yes.
Okay. I'm gonna put a little question mark here. Did other people get that? Okay. 22.3?
Yeah.
All right, well, we'll see, we'll have to see which one of those is correct. Or if either of them are. So, first of all, I'm just going to write my initial kinetic energy plus my initial potential energy is equal to my final kinetic energy plus my final potential energy. And I can do this because the only work done is clearly due to gravity, right? The only force on it. So my kinetic energy initial is 1/2 m v initial squared. That's at 20 meters per second squared. My potential energy initial, let's call my height equals 0 being the ground. And then I start out at 10 meters above the ground. So I do v times 10 meters. It's going to be equal to my kinetic energy final, which is 1/2 mv squared,
Plus
v final squared, plus my potential energy final, and it's at 0, right?
Yeah.
Height, so that'd be
That's
0.
height.
One of the nice things about the gravities, notice all the masses cancel out if I divide through by m. So I get 1/2 times 20 meters per second squared, plus v times 10 meters is 1/2 v final squared. So this is 400 meters squared per second squared too. So that's, well, actually, I'm just going to multiply both sides by this by 2, okay? 1/2 with 2 here. See what I did? So this would be 400 meters squared per second squared plus 2 times g is 19.6 times 10, 196. So v final, square root of 596 meters
24.
squared per second squared, which is
24.4.
24.4 meters per second. Neat? All right. Now, ready to do one more? And then we'll do the roller coaster one. One more. Okay, this time. See if we can do this. So a car with no friction on its wheels, so only work is done by gravity. is traveling with an initial speed of 20 meters per second. It goes down the hill with a height of 100 meters and goes back, and then there's another little hill up here with a height of 20 meters, and then distance from the ground, 0. What's its speed when it's on the top of this hill? So see if you can get that. But it should be correct. Okay, let's go through it. What do you guys get? How much?
44.4.
Yeah.
What?
44.44.
All right, let's go see if we can get this. So the kinetic energy initial is 1/2 m the initial squared. The potential energy initial, which is 20 meters per second, right?
Yeah.
Squared. The potential energy initial, well, It depends on what we want to take our 0 point of our height to be. For the time being, let's just take the bottom of this, h equals 0, okay?
Okay.
And then I'll show you that if I just take this end point as h equals 0, it's kind of easy. Doesn't really matter. So in this case, we would get mv times 100 meters is equal to the final kinetic energy plus the final potential energy.
Is what you're saying.
Okay, like that, right? The m's cancel out. So divide every term by m. And I can multiply every term by 2. So I see that 20 meters per second squared plus 2v times 100 meters is equal to v final squared plus 2v times 20 meters. I can subtract this 2v times 20 meters from both sides, right? So I get 0 here. What would this become? So 2g, well, let me subtract it from both sides. So I get minus 2v times 20 meters
What did you subtract?
is equal to v final squared. I just subtracted 2g times 20 meters from both sides.
Oh.
Notice that this is 2g times 80 meters. Okay? And I would have gotten this right from the beginning if I took this final as my height equals 0. Doesn't really matter what you pick your 0 point of your height to be. And but this works, so I get 20 meters per second squared plus 2g times 80 meters is equal to v final squared. So take square root of this whole side. And what do you get? If I plug in numbers, I should get that 44.4. Good? All right. Now let's do one more. This one combines a little bit. And it's important for the Hot Wheel enthusiast. All right. Let's say I have let's say that I have a Hot Wheel track like this. And I'm dropping a Hot Wheel car from a height. And I want to see what the height is that I have to drop it from in order to get it around a loop with a radius r. This, by the way, will remind you a little bit about circular motion. So, at the top of this track, in order for it to stay on the track, what's the condition? That the normal force didn't go to 0 before right at the top of the track.
They're both.
So the minimum speed it could be getting around this track occurs when the normal force right at the top is 0. Now if it's a circular track, what do we know about the condition for it to be moving in a circle?
There is acceleration.
And what's the acceleration?
Centripetal acceleration.
And what's the formula for that?
V
Square
squared
over
R.
R.
That's right. So if I draw a free body diagram here, I have one force on it if the normal force has just gone to 0. And that means mv has to be mv squared over r, right? Okay. And this is a condition for the minimum speed that it can get around the track. So if I want to figure out the minimum height I can drop this from for it to get around the track, I'll use this minimum speed. Does that make sense? If I drop it from a higher height, it'll probably be going faster there. So, I just have to be higher than the height I'll find. Okay. So, what's the height above the ground at this point, when it's up here? 2R. Okay. So the height above the ground is 2R. So what I'll find is, let's just figure out what the speed is up here, okay? Or what the kinetic energy is up here. Find KE here. Well, I'm going to use my kinetic energy initial plus my potential energy initial is equal to kinetic energy final plus potential energy final. This works because, once again, normal force doesn't do work because it's perpendicular to it. I'm assuming no friction, perpendicular motion. So, so if I drop it from rest, this will be my initial point. This will be my final point. What would be my speed? 0. So 0. mgh, right, is what the initial potential energy is. Kinetic energy is 0. That would be equal to my final kinetic energy plus my potential energy final, which is mg times 2r. Right?
So wouldn't you write 1/2 mv squared kinetic?
Yes. 1/2 mv squared. All right. Now, let's look at this thing here. I need mv squared to be at least mg times r, right? So if I solve this equation for r, I get mgr is mv minimum squared. That means this mv squared here, I can substitute it in there, right? Figure out the minimum height. So I could get mg is equal to 1/2 times mgr plus 2 mgr. See what I did? Kind of tricky. I said, okay, this is my condition for circular motion, just barely staying on the track. That gives me what an mv squared has to be. Just put that into here, where it was in the kinetic energy equation.
So did you just put it just in the mv, in the m, or for the mv?
Just
Okay.
that thing. Okay. So 1/2 mgr plus 2 mgr. That's 2.5 mgr or 5/2 mgr, right? Okay, so I have this is equal to this. I can divide both sides by an mg. And I get that the h is 5/2 r. That's the minimum height I can drop it from in order for it to make it around the loop. If I had a bigger height, it should be able to make it around better. If I dropped it from less than that, it would fall off the track beforehand.
So what if you asked us what's the maximum height
What's that? There's no maximum height.
that you could drop? Oh, okay, yeah, you could drop.
Yeah, it'd be going faster and faster. You just would have more normal force. Yeah. Now, at some point, you'll probably break the track if you have too much normal force, so there probably is a maximum height. But, yeah. Okay, 2 mgr plus 1/2 mgr is 4/2 plus 1/2 is 5/2. Good, all right.
No, okay.
What's that? I don't know.
Also, it's what we just did. Okay, I tried to give you the and I couldn't, so that's probably why. I was like, doesn't he have to give you the math? Okay,